Okay, you can begin now.
Sure. So good afternoon, everyone. So I'm very pleased to announce our next speaker for Special Functions and Number Theory seminar, Dr. Neelam Saikia from University of Virginia. So Neelam did her PhD at IIT Delhi in 2016. Right. And now she is currently a Fulbright Nehru postdoc at University of Virginia. So she'll be presenting her joint work with Ken Ono and Hassan Saad. Right.
So may I go ahead?
Sure, please. Yeah.
So I would like to thank the organizers for this nice introduction and for giving me this opportunity to present our work here. So today I'll be talking about distributions for Gaussian hypergeometric functions. And this is my joint work with Professor Ken Ono and his PhD student Hassan Saad. So first of all, we motivate you by giving you an example of a theorem. So basically, so to motivate, so this is a theorem which is very famous, and it is very famous theorem in arithmetic statistics. So to see this theorem, so before going to this theorem, we first give you an example. So this example basically counts the traces of Frobenius of an elliptic curve over a finite field. So for example, if you consider this elliptic curve E, which is defined by this y square minus y is equal to x cubed minus x square, then for each prime p of good reduction, if you consider this number AP, which is defined by p plus 1 minus number of points on this elliptic curve over the finite field FP, then there's a famous theorem by Hassa which gives that this AP is lying in this interval. The interval is minus 2 square root of p to 2 square root of p. And if you divide this numbers AP by 2 square root of p, then this number lies in this interval minus 1 to 1. So if we consider all these numbers AP by 2 square root of p, so this is some kind of normalization of AP. So and if you consider the values of this traces of Frobenius for the primes up to 1 million, then you get this picture. So this looks like some kind of squares semicircle, and which is bounded by square root of 1 minus x square. And and it gives the graph of 2 by pi square root of 1 minus x square. So this clarifies some kind of theorem which is very famous in number theory, which is known as the SATO-TATE conjecture. So this conjecture is about elliptic curves over finite field, which has no complex multiplication. So I'll just go quickly for this conjecture. So if E over F over Q is an elliptic curve without complex multiplication, then we can define this angles theta p, which is lying in this interval 0 to pi by this formula, where this theta p is somehow connected to the trace of Frobenius that we have defined earlier. So since the trace of Frobenius AP is lying in this interval minus 2 square root of p to 2 square root of p, so we can always find an angle theta p. So, and we define this angle like this. So then for every real number alpha beta, which is lying in this interval, that is, if we consider this closed interval alpha beta, which is contained in the interval 0 to pi, then if we count the primes up to x such that this theta p, this angles lying in this interval alpha to beta, and when we take x goes to infinity and we compare this ratio of these angles and the primes, then we will obtain that this converges to this definite integral of alpha to beta sine square beta. And this conjecture was open as I think it's about it's open till I think around 50 years, and then this conjecture was proved by Taylor and his collaborators, and this conjecture is is very deep in, and the thing is here, this is kind of they apply some kind of hard techniques to prove this theorem. And this theorem is so important that in this area, I think around more than 100 papers have been written in this area. And the thing is, this is not not only about elliptic curves over finite field. So the thing is, the SATO-TATE conjecture is true for elliptic curves over totally real field or totally real number field without complex multiplication, and not even only for the elliptic curves. This there are some results which assert SATO-TATE for abelian varieties, and in some completely different direction, the SATO-TATE is true for the modular forms, mostly like Hecke eigenforms, which has no complex multiplication. So yes, so yeah, so yeah, so here we are not going in that direction. We are asking some three general questions here. So so first we would like to study the first question, which gives that are there analogous results for other families of varieties which are kind of SATO-TATE? Or then we could ask like in every variety, can we get like a semicircular distribution like we have in a SATO-TATE case? And frankly speaking, we would be disappointing if we get semicircular all the time. So if they are not semicircular, then how exotic they can be? And then we would like to study, is there a structural framework explaining the other distributions, the framework that is different from the earlier that that applied that applied to prove the original SATO-TATE. So of course we cannot have one structural framework which gives all the distributions for varieties. So here we want to establish, is there any structural framework which is different from the earlier work? So our goal is to study three different families of hypergeometric varieties. So first we define what is a hypergeometric function. So this hypergeometric function is a formal power series. So if we have these numbers, alpha 1, alpha 2, alpha h, comma beta 1, beta 2 up to beta. So if these are complex numbers, then we define this hypergeometric function in the classical setting as this formal power series. So this definition was is long time back. It's given by Gauss. And yeah, here the symbols here appearing is known as the rising factorials, and these are defined like this. So if the suffix n is 0, then we define this as 1. And if it is greater than or equal to 1 suffix, then this is defined as this rising factorials. So this hypergeometric function is known as classical hypergeometric function. And any variety which is connected to somehow connected to this classical hypergeometric functions, which are I think kind of known as hypergeometric varieties. So yeah, so the hypergeometric varieties we would like to study in our work is Legendre form of elliptic curve. So here the role of Legendre form of elliptic curve is like that. So if we consider this elliptic curve, which is known as this Legendre form of elliptic curve because of this linear factors. So if we have this lambda, which is a real number which is lying between 0 to 1, then the real period of this Legendre form of elliptic curve, so this real period is given by this 2f1 classical hypergeometric functions. So yeah, where these parameters involved here is 1/2, 1/2, then 1, and this lambda. And this classical hypergeometrics is connected to this this normalized value of this real period of Legendre form of elliptic curves. So this is a kind of variety we'd like to study in our case. So it is not always true that you always get a get this kind of function for all the kind of varieties. I mean, it is not true for elliptic curves. It is always difficult to find such kind of function. So recently in 2010, McCarthy studied a Gaussian form of elliptic curves, which is given by this form. And this forms look like this legendary form, but they are very much different in their structure. So so McCarthy studied this form of Gaussian form of elliptic curve, and he obtained that for lambda greater than 0, the real period of this of this elliptic curve can be expressed in terms of this 3f2 hypergeometric function. So here it is false if we can say that the period is related to this hypergeometric function. In fact, the square of the period is related to this 3f2 hypergeometric function, and it is much difficult because the square is related to this 3f2 hypergeometric functions. So these two hypergeometric functions are important in our study because they have connection with elliptic curves. So yeah, in our work, we would like to study these two family of elliptic curves along with this this K-tree surface, which function field equation is given by this. So these three are the varieties we would study in our work. Okay, so now we go to we go for Gaussian hypergeometric functions. So here, Gaussian hypergeometric function is defined by Green. So this function is defined analogously with classical hypergeometric functions. So let me just quickly give the definition. So if AIs and BIs, so if these are multiplicative characters of the non-zero elements of the finite field FQ. So here FQ is a finite field. So then with these parameters AIs and BIs, the Green defined this hypergeometric function in this finite sum of this character sum. So this is so here you can you note that so in classical hypergeometric function all the parameters are complex numbers. But in Green's hypergeometric function, this parameters are replaced by multiplicative characters. So here, this is all about Green's imagination. And the thing is here, it is not arbitrarily come like in this way. So of course, there are some motivation. So Green's what Green follows here is that he first considered for the 2f1 function, he considered the integral representation of classical hypergeometric function, and he used some analogy, like he replaced the integral by some discrete sum over the finite field, and the powers become the character sums. So yeah, using that analogy, Green defined the 2f1 hypergeometric function. And we know that the characters of a finite group is linearly independent. So any function on FQ star. So any function on FQ star, we can write them as character sums with some coefficients, and ultimately when we use orthogonality relations of the characters, we obtain this kind of coefficients. And the coefficients that appear here is not an arbitrary coefficient. This is well defined. It is defined as the normalized classical Jacobi sum. So here, if you forgot what is a Jacobi sum, so it is like sum of all x and evaluated at a of x and b bar of 1 minus x. So this is a normalized Jacobi sum. So this Jacobi sums appear here in the definition of Green's function. And we now fix some notations for our further talk. So if Q is a prime of if Q is a power of a prime whose characteristic is different from 2, then we denote phi a character of order 2 and epsilon. So this denote the trivial character. Then we use this notation, this n f n minus 1, which is suffixed by q. So it's defined as this Green's hypergeometric function, where this function involves only trivial and quadratic characters. And here it is important to note that we use the suffix q here every time, just to make sure that we are in finite field setting. Whenever we use this notation q, so it is guaranteed that we are in the finite field setting. Okay, so this is our notation for the rest of the talk. So now we will explain one mantra. It's known as the arithmetic and geometric mantra. So many of us who work in this area might be seeing this many times. So whenever we have a classical hypergeometric function in this, which is defined in this way, and whenever we have a connection with this function with the real periods of elliptic curves, so we can find an analogous result in the finite field setting, which where this halves are replaced by this quadratic characters, and the one are replaced by this trivial characters. Then in this finite field case, this function is somehow related to the traces of Frobenius of an elliptic curve. So this is the traces of Frobenius of an elliptic curve. So so this is the mantra we are going to play. So so that whenever there is a real period, we'll obtain similar kind of result in the finite field setting. And the thing is, this mantra is not always true that like we always get this kind of results, but somehow in our work it plays an important role. Yeah. So more precisely, we would say that, so if FQ is a finite field whose characteristic is different from 5, who's different from 2 and 3, then for any lambda which is lying in this set, then we obtain that the traces of Frobenius of the legendary form of elliptic curve is expressed by this 2f1 Gaussian hypergeometric function. And again, we can obtain that the number of points on the K3 surface is given by this 3f2 hypergeometric function. And here this 3f2 function appear 2 times again for the 3f2 hypergeometric function. So this is related to the square of this traces of Frobenius of the Gaussian form of elliptic curves. So yeah, so this is a kind of relation we work in our case. So if you remember that, so we have previously talked about how the periods are related to the classical hypergeometric function. So this is the mantra that played here. So if we have a period represented by this 2f1 hypergeometric function, then here we have this 2f1 Gaussian hypergeometric function, where this 1/2 is replaced by the quadratic characters and 1 is replaced by trivial character. And like here we have 3f2 classical hypergeometric function, which represents the square of this period. Then here we also have the square of this trace of Gaussian form is related to this 3f2 hypergeometric function. So this is the mantra that are going to play in our work. Okay, so in our work we would like to study the distributions of 2f1 hypergeometric function. So if we renormalize this value, this 2f1 by this, then we obtain that this always lying in this fixed interval -2 to 2. This interval doesn't depend on the length of the it just doesn't depend on the size of the finite field. So if we renormalize these values of 2f1, we obtain that this lying in this interval. Then we would like to study what is the distributions for this hypergeometric function. And here we have our first theorem. So if A and B are numbers that lie between -2 to 2, and R is a fixed positive integer, then the ratio of this lambdas such that this value of this renormalized value of this hypergeometric function live in this interval AB. And if we consider this ratio where when we take p goes to infinity, we obtain that this converges to this definite integral. of square root of 4 minus t square. And in other words, we can say that this is the distribution is semicircular. So here we have the picture. If we consider the histogram of the two F1 values for primes 93,283, then we obtain that this kind of histogram, which is like kind of semicircular. So for the 2F1 case, we obtain distribution is semicircular, which is kind of analogous to the original SATO-TATE. So we would like to make a remark here. So that the thing is the Legendre form of elliptic curves over large finite fields. So this behave like original SATO-TATE that we have earlier by the work of Taylor and his collaborators. Yeah, and for the 3F2 hypergeometric function, so if we renormalize this value of this function, then we obtain that all these values are lying in this interval -3 to 3. And in our second problem, we would like to study the limiting distributions for this hypergeometric function. So here we have our second theorem, which gives that if A and B are two real numbers, which is lying between -3 to 3, and R is a fixed positive integer, then we obtain that the limiting distributions of this renormalized value of this 3F2 function, such that the value lying in this interval AB, then this limiting distribution is converges to this definite integral of f of t, where f of t is defined in this way. So this looks like Batman distribution. So why do we call this Batman? So it will be clear from our next picture. So if we consider the histogram for this 3F2 values up to primes 93,283, then it looks like a Batman. So that's why we call this as a Batman distribution. Yeah. So now our problem is to find distributions of these two functions here. So to do this, we adopt the method of moments. And in this method, so what we compute, so we first compute the power moments for these two functions. And once we have the power moments, we will find their asymptotic formulas as q goes to infinity. And then once we have the asymptotic formulas for those moments, we will compare these moments with the moments of the random variable of our claim distribution. So to have the 2F1 moments, what we are obtaining is that, so we will obtain that the moments for these two functions, 2F1 and 3F2, we obtain that these moments so these moments can be expressed in terms of weighted sums of class numbers. So let me define what the class number here is. So if -d is a negative discriminant, then h of -d, so this is the actual class number of the imaginary quadratic order having discriminant -d. Then their Hurwitz class numbers are defined in these two ways, where of course there are two types of Hurwitz class number. So in the first type, what it is defined as it is defined as the intermediate class numbers of these orders, where the sum runs over all these intermediate orders starting from the order O to the maximal order. And in the second Hurwitz class number, which is denoted as h star of d, so this is same as like this, but it's weighted by this omega. So it is also the intermediate some of the intermediate class numbers weighted by this omega, where this omega denotes the half of the number of roots of unity in an order O prime. So yeah, so while computing the 2F1 moments, we end up having several cases. So here in the first two cases, we explain the even moments. So, and this even moments depend on R. So if R is odd, that is R is the power of the like p to the R, which is like the order of the finite field. So if R is odd, then we obtain that this even moments. So these are expressed as this weighted sums of this class numbers. where the sum runs over all these traces of phobenius of an elliptic curve, which are co-prime to P, and which satisfies this congruence condition. This congruence condition is totally group theoretic. We'll see later why this condition appear here. And similarly, if R is even, then this then the even moments for this 2f1 function is we have an analogous sum like this, like in the previous case, with an extra constant term appearing here. And this constant term is not an arbitrary constant. Of course, it is well defined. So here, this constant SP, so it is defined as it's defined as the degree of the characteristic P super singular locus, and it is approximately equal to P over 12. And here the constant CQ, so this is a rational number lying between 0 and 6. And it could be understood as the average of the number of legendary normal form of elliptic curves in an FQ isomorphism class whose traces is equal to plus or minus 2 square root of Q. So here the constants CQ and SQs are well defined. And these are some bounded constants, CQ and SQ. Okay, so for the odd moments, so for the odd moments, this condition is depend on the congruence condition on Q. So if Q congruent to 1 mod 4, then the odd moments for this 2f1 hypergeometric functions. So we have an analogous formula like this, and which we won't show you here because of lack of space. And yeah, if Q congruent to 3 mod 4, in this case we are lucky because the odd moments end up being equal to 1. So here there is no class number. All right. So yeah, so the phenomena that works here while computing these moments is that we make use of the theory of complex multiplication explicit for elliptic curves, and this goes back to the work of Turing. So we know that every elliptic curve over FQ has complex multiplication, and this the CM order generally varies with respect to P. Otherwise, we call E has global CM. And basically, in our calculation, we count the number of isomorphism class of an elliptic curve over a finite field with some fixed stress and with some prescribed subgroup. So here we basically define this number IGSQ, with this the number is defined as the number of isomorphism class of an elliptic curve whose stress is like this, and which has the fixed group like this. EG is contained in this group, and we denote this number by IGSQ. And this number is known for G equal to Gn times Gn. This number is known by Scoop's theorem. So here, if the trace is co-prime to P, and we have this two additional congruence condition, where this first condition is totally group theoretic, because here if G equal to Gn times Gn, then the square should divide the order of the group. So that's why this n square divide this number, and with this additional congruence condition, we obtain that this number I, which like the isomorphism class of elliptic curves, which contain this subgroup Gn times Gn. So this is given by this class number, and this is the Harvard class number that we have defined earlier. So yeah, so we can see from here, we can see, so if we put n equal to 2 here, then we obtain 4 divide q plus 1 minus s, and this condition that we were talking about in our moments, we have such condition on S such that S congruent to q plus 1 mod 4. So this condition comes from here, and here in the class number we have 4q minus S square up in 4, and you can see, as you can see earlier, that in most of our moments formulas we have this kind of class number appear in our moment formulas. All right. So now we'll give a quick sketch for the proofs of 2f1 moments. So basically, so we have to use this certain facts. So it is always true that that this group Z2 cross Z2, so this is always contains in the group of rational points of this legendary form of elliptic curves over this finite field FQ. And we always have a map, 6-to-1 map, which maps this 6 values of lambda. This maps to the same J invariant. So since they are mapping to the same J invariant, so the legendary normal form of elliptic curves, which are where these lambdas are coming from the set, are either isomorphic to each other or they are at least quadratic twist of each other. So we use these two facts, and yeah, using these two facts, we organize all the legendary form of elliptic curves by their FQ isomorphism classes. And once we have the classes, we apply the Scoop's theorem, and after some kind of detailed calculation, we get our 2F2 moments. Now for the 3F2 moments, so we did similar kind of calculation, but somehow in a different manner. So here we have the 3F2 moments. So it is important to recall that we know that the Gaussian form of elliptic curves is related to the square. The square of the trace of Frobenius of this Gaussian form elliptic curve is related to this 3F2 hypergeometric function. So for the 3F2 hypergeometric function, so here we need to obtain the even moments only. So since the square of this trace is related to this hypergeometric function, so here it is important to collect all those lambdas for which this Gaussian form of elliptic curve has trace equal after sign. So here we did exactly the same. So we collect all those lambdas for which the Gaussian form of elliptic curve has the trace either S or minus S, and we take their even power. So ultimately, they are all the traces are equal in this set. If we consider all these lambdas for which this is the trace would be plus or minus S. So if we take the even power, all are equal, and we add those traces, and we obtain that this can be expressed as the size of these two sets. Where these two sets, ISQ and I2SQ, are defined in this two way. So here ISQ, so this is the set. So it gives the isomorphism. So it is the class of isomorphism, class of elliptic curves of elliptic curve over FQ, whose trace is given by plus or minus S. And I2SQ, so this is a subset of this set ISQ. So it contains all the classes from this set whose two Gaussian points are given by this subgroup. And of course, by Scoop's theorem, we know the sizes of these two sets. So here, when we apply Scoop's theorem, we obtain this sum as in terms of class numbers. So similarly, in the second sum, we obtain what we are having here is we consider the same sum but weighted by this phi of minus lambda. So phi of minus lambda is kind of legendary symbol. It's like phi of minus lambda is 1 whenever minus lambda is a square, or otherwise it's -1. So if we consider this weighted sum, then we obtain that this sum can be expressed similarly in the sizes of these two sets. So using this theorem, we obtain our even moments for this 3F2 functions, which is eventually gives in terms of weighted sums of class numbers after applying Scoop's theorem. So yeah, so like we have mentioned earlier, so our method is to first we will determine the moments, and then once we have the moments, we will obtain their asymptotic as Q goes to infinity. So yeah, so we have the theoretical moments for this for these two functions as weighted sums of class numbers. So now our job is to obtain the asymptotic formulas for this moments as Q goes to as P goes to infinity. So here comes the famous theorem of Jagier. So what he proves that if we consider this sum, where this sum is look like the generating function of the class number, and this indefinite gamma integral. So if we consider these two sums, so this behaves like so this function behaves like 3/2 harmonic mass form on this gamma naught 4. And this Jaggier's function is very important in our work, because we are going to apply this function to compute the asymptotic formulas for this moments. So here we will recall one famous theorem by Eclair. So what he did actually, so he considered this sum of this class numbers, where the sums runs over this numbers like s lying between square root of n less than or equal to square root of n. So if we consider this class number, then we obtain that this class number can be expressed as this kind of divisor sums, where sigma 1n is the divisor sum and gamma 1n. So it is defined as some kind of counts the minimum divisors of n, which are less than n by 2. So this this sum of class numbers is expressed in these two sum. So why this is important in our work? So here you can note that. So if we consider this character sum, so ultimately when we have s congruent to q plus 1 mod 4, so that means s is even here. So if we consider all the traces, like here traces are like two times of s. So if we remove this factor 4 from here and here, so we get that this sum will exactly behave like this sum. And here we have the weight as s to the m. So here if we have if we have m equal to 0 here, then we obtain here this sum behaves like this Eclair sum. And here it is, since this sum is expressed in this way, in kind of divisor sum, so we can somehow obtain that this is q plus small o of q. So yeah, we are very close to our asymptotic formulas. So yeah, so here for m equal to 0, we have this is analogous to, I mean, it's exactly equal to the Eclair's. So here we are kind of generalizing this theorem. So if we can bound this, as q goes to infinity, so we'll get our asymptotic formulas for these moments. So yeah, so now we are focusing on for other values of m to obtain this asymptotic formulas. Yeah, so the method we apply for obtaining the asymptotic formulas. So here we apply the Cohen-Rankin bracket operator. So let me just define what's this operator. So if f and g are two modular forms of weight k and l, and these are not necessarily holomorphic, then for every nu greater than or equal to 0, then the Cohen-Rankin bracket is defined in this way. So this is a finite sum, where this sum is runs over all the integers, summing up to nu, and with this coefficients, and here, and this is the derivative of f, r derivative of f, and s is derivative of g. So yeah, so if we combine all these derivatives, we obtain this operator, and this operator plays an important role in our work. So why it is important? Because if f and g are modular forms of weight k and l, then if we apply the Cohen-Rankin bracket for this pair of f of modular forms f and g, we obtain again a modular form of weight k plus l plus 2 mu on the subgroup gamma. So here this operator can be described as like the operator which produces modular forms like that. So yeah, so how do we obtain this asymptotic moments? So here we briefly give the steps which we follow for obtaining this asymptotic formulas for these moments. So here we apply the Cohen-Rankin bracket for the Jaggier's function and these two theta functions. So this is a theta function of weight half, and this is theta function, it's like the Dedekind eta function of weight 3 half. So we apply Cohen ranking bracket for this pairs of functions, and of course they are non-holomorphic modular forms where the coefficients involves the weighted sums of class numbers. So after making a careful steps for while counting this coefficients, so we obtain that this is a non-holomorphic modular form. So our job is to make this modular. So we apply the holomorphic projection for this Cohen brackets. So once we apply this holomorphic projection on this bracket, it will become a modular form. And when this becomes a modular form, we apply Martin's theorem, Martin's proof Cohen's conjecture, which basically gives produce modular forms. So once we obtain this holomorphic projection on this pair of Cohen ranking brackets, we obtain modular forms. So once we have the modular form, so here note that in all the expressions of the modular form, we have somehow this weighted sums of class numbers, because we use Jaggier's method, Jaggier's function. So in the coefficients, we obtain the weighted sums of class numbers. So then finally we apply the Billing's theorem, which bounds the coefficients of modular form. So once we have the bounds, we will obtain our asymptotic formulas for this moment. So this is kind of the method we apply to obtain the moments, the asymptotic formulas for this moments for both 2f1 and then for 3f2 functions. Okay, so yeah, after a lot of calculations, like 20 pages, we obtain this theorem, so which gives that if R and M are positive integers, then when we take P goes to infinity, we obtain that this moments converges to this. If M is odd, then it converges to 0, or otherwise we have this kind of, or if M is even, then we have this Catalan number here appearing. So it somehow gives the it's kind of look like original SATO-TATE. And yeah, and if and for the 3f2 functions, if we take this limit as P goes to infinity, we obtain that odd moments are 0, and when we consider the even moments, we have like this sum of weighted sum of this Catalan numbers. And here it is important to note that this moments ultimately behave like a classical hypersymmetric function. So yeah, when we have the asymptotics for this 3f2 moments, we are obtaining this classical hypersymmetric function. Yeah. So now we briefly give what's the criteria for the distribution. So it is a general question to ask. So whenever we have a function from the finite field fq to this -1 to 1, so what can be said about the distribution of this function? So here we apply the method of moments. So using this method, we obtain these two lemmas. So in the first lemma, we obtain that. So if we have the moments which looks like this, like for odd moments, we have moments end up being equal to 0, and when M is even, these end up being equal to the Catalan number. And yes, when we consider the limiting distributions of the renormalized values of these functions, then we obtain this kind of integral. And in the second lemma, we obtain that if we have moments, if we have the moments like this, then the limiting distributions of the renormalized values of this function is converges to this integral, yeah, where ft is given by this function. Yeah. So yeah, so we obtain some new distributions in this direction. So yeah, so if we consider the renormalized values of these 2f1 functions, So then the distribution of this function is semicircular. And for the 3f2 functions, if we consider the distribution of the renormalized values of these 3f2 functions, it will behave like Batman. So yeah, so here we have the summary. So we can say that for Legendre normal form of elliptic curves and for Cauchy form of elliptic curves, so here the distributions are semicircular, where for the K3 surfaces whose Picard number is greater than or equal to 19, so we have the Batman distributions here. So here are the pictures again for P equal to 93,283. So we have this distributions. Thank you.
Thank you very much, Neelam, for a very interesting talk. Are there any questions? Okay, Neelam, I had one question. So you may be knowing that Ramanujan had alternative theories of elliptic functions, where he replaced the classical hypergeometric function 2f1 of 1/2 1x by 2f1 of 1/3 2/3 1x, or 1/4 3/4 1x, or 1/6 5/6 1x. So there are corresponding theories of elliptic functions which have its origins in Ramanujan's lost notebook. There are a few reasons, and people have now worked on it and have developed the corresponding theories of elliptic functions. So do you know of any study where people have worked with these ones with the alternate parameters like 1/3 2/3?
Yeah, like for the like in the finite field setting, if we replace the 1/3 and 2/3, then one obvious replacement would be like for like a character of order 3. So if you replace that by a character of order 3, like if you consider the Gaussian hypergeometric function for which involves characters of order 3, suppose it is a chi3. And the next would be chi3 bar, which basically represents like, which is analogous to 2/3. And on the bottom parameters, we have epsilon. Then they are connected to the traces of Frobenius of an elliptic curve. I think it is related to I think it is related to this which form. I think somehow some modification of the Weierstrass normal form of elliptic curve, if you consider with some special value, then we obtain that the traces of Frobenius are represented by those Gaussian hypergeometric function. And in fact, if you consider, I think 1/5 and like 1/5 and like yeah, and what are the other I think 1/12 and 5. If you consider 1/12 and 5/12, then I think if you consider the analogous hypergeometric function which involves characters of order 12, then you also have such kind of representation which gives traces of Frobenius of some special forms of elliptic curves. So they have some analogous theory.
Okay, thanks.
Ahmed had a question in the chat.
So how do I open the chat?
Ahmed, maybe you can just ask the question.
Maybe I stop sharing. Maybe I think I can. Okay. Oh, like for so any a book like for the distribution, you can for the distribution part you can read the paper by Birch, which gives like flavor of the distributions for this elliptic curves over finite field. So this is kind of the base paper in our work by Birch. For Taylor and his collaborators, the thing is, it is very difficult, and frankly speaking, I haven't seen the proof because it's very difficult in that setting. And for elliptic curves, you can see the books for this arithmetic of elliptic curves by Silverman. This book is like kind of very well known. And for hypergeometric functions, for classical hypergeometric function, you can go for the books for like spatial functions by Aske and some other authors. this kind of a basic for this books. And in the finite field setting, there is no any book. You can follow Green's paper, which like it's titled as hypergeometric function over finite field. So I think these are some basic reference for this talk.
Any other questions? If not, I request everyone to unmute and clap for a nice talk by Neelam.
Yes, indeed. Thank you.
Thank you.